Hi again. We continue to talk about multiple regression, in particular with the ANCOVA model, because an experiment is not always allowed in terms of time and money. We use various modeling strategies. ANCOVA is one of them, modeling strategies. So remember this term, statistical control. Okay, one way, okay, the page 5 is about design control. Design control. Let's read one by one. One way to exert such control before collecting data is to really hold the covariance constant by forcing all subjects to have the same value of the covariance. Here, the same level of private education cost, which is a proxy of SES, socioeconomic status. So the parents are richer than the other. I mean, parents are rich, then they will spend more money on the kids' education, right? So private education cost is a proxy of SES. If we think we'd like to control for private education cost, we could select only students with, say, 10K of the expense in the private education of interest. Yeah, we can selectively collect a specific class of the people. Another related design control is blocking. I mean, all depends on your research question. If your research question is only focused on the target population of 10K income people, then you would do it, right? But you do not generalize your study result to entire population because you collect the data only focused on the income level 10K, right? Okay. So, you need to justify your activity based on what you are planned to do. Another related design control is blocking. In blocking, including randomized blocks designs, we select students with different levels of the private education cost, but we would assign equal numbers of students with each level of private education cost to each treatment group. This is a little bit better than the first method, right? Not just the 10K people, but all kind of different level income people. And then you have the cell, 10K people, 20K people, 30K people. You assign the same number of people, regardless of the average income level. You select the same number of the people to assign each cell, block. This is often called a design control. So you design this before you collect the data, because we are controlling something by the way we design our study. However, both of these can be very hard to accomplish. Both require that we know a lot of information about our potential subjects before we select them. Yeah, these two techniques are still not experiment. So let's think about it. Experiment. Experiment means full of researcher's control. So researcher has an intervention, and researcher assigned the intervention to certain people. I mean, by flipping a coin. Yeah, if a person has tail, then the researcher assigned the person to a treatment group. And then if the coin is just the head, and then treatment group, something like that. control group, treatment. Just mechanically, you assign the people to either treatment group or control group. This is experiment, you know. And flipping a coin means randomization. But in this case, you know, randomized blocks designs are much better than convenient sampling. However, it's still far from experiment. I mean, it's closer to experiment rather than just statistical control. I hope I'm not confusing you. So I try to deliver the message, the difference between the design control and statistical control. Okay, you can mix up design control with the statistical control in the one modeling strategy. You know, in your design, you can mix the method like that way. You know, but what I'm trying to say is, if you have just collected data, what you're gonna do is just the statistical control. Find out the theories for supporting your model, and then include all the important X variables on the Y outcome. And you shouldn't include the irrelevant X variables in your model. That is a model specification. And then based on that multiple X variables, you control, you will get the adjusted mean difference among the, you know, subgroups, controlling for all other factors, X variables. So this is a statistical control. But if you have this kind of design control in your ANCOVA model, it can be better. It can be better, right? But again, design control is much more expensive than statistical control because, you know, this is planned before you even start to do the collect the data. Okay, so in the social sciences, you know, sometimes experiment or this kind of randomized block design is not allowed. Sometimes randomization, you just assign some kind of medicine to people. It can be unethical or not feasible in reality. So we just need to, we have to use, survey data, observational study data. So we need to know a lot of, statistical control strategies to use the survey data better. Okay, all right. ANCOVA allows us to control covariates statistically, yes. And we don't need to info on the covariates before we create or collect data from groups. This analysis technique gives us results that allow us to estimate what the group means on our outcome would have been if the groups had the same means or were equivalent on the covariate. These so-called adjusted means removed the effects of X from the Y scores of all of our subsets. The language we use here is very similar to the words used to talk about regression result. Indeed, we use a form of regression to do the ANCOVA. All right, so as we have regression assumptions, this special form of regression, ANCOVA, also has its own assumptions. So let's look at the ANCOVA assumption now. First, the covariate X, continuous variable, should be linearly related to the outcome Y. Yes, we have XY linearity assumption, right? Number two, if there is a treatment involved, we also have to know that the treatment did not affect X. And similarly, that X did not affect the treatment. What is this talking about? Do you remember multicollinearity, right? So among the multiple X variables, we do not want to have a high correlation among them, right? That is called multicollinearity. Okay, if multicollinearity issue is not satisfied, we will have a very fluctuated standard error, and then that makes our estimate test value is biased. Number three, a third key assumption of ANCOVA is that X relates to Y in exactly the same way for all of the groups in our analysis. So we want to control private education cost with the same mean of the private education cost, and we're gonna compare the three race ethnicity groups math scores, right? But what if your covariate private education cost cannot be commonly shared by the three different groups? If you cannot have one common mean of the covariate for three groups of race ethnicity groups, ANCOVA is not working. So if this assumption is especially important, otherwise ANCOVA analysis is not valid. Also, especially, we can say that there should be no covariate X group interaction. So, do you remember the formula? I mean the equation for ANCOVA? So Y hat equals beta 0 plus beta 1 x1 plus beta 2 x2. This is the ANCOVA model. If you include beta 3, which is interaction between x1 and x2, then this is a different model than not ANCOVA model. Okay? So one of the assumptions in ANCOVA, it should not have interaction effect. It should not have interaction effect. If your theory, I mean, you have your research hypothesis, and your research hypothesis was set up by supporting numerous theories, let's say so, then your theory should not say interaction between x1 and x2. Then you can set up ANCOVA model. If your theory says, oh, interaction between x1 and x2 is possibly done, then you have to have one additional model, not ANCOVA model. So interaction model is called ATI model. We will talk about it later, but today we just want to talk about ANCOVA model, okay? So ANCOVA model, remember three assumptions. This is a three additional assumption, right? We already learned the regression assumptions. They are basic, and then we add more assumptions to this special form of regression, which is ANCOVA. So number one is covariate. Your covariate continuous variable should have a linear relationship with Y. And number two, shouldn't have a collinearity between x1 and x2. Treatment is x1 and x2 is continuous variable. And number three is no interaction. And also, this first part is kind of, you should have a common mean of covariate for the entire groups, subgroups, okay? X1 in ANCOVA is often used when the grouping variable or factor is not a treatment at all, but rather some kind of status variable like gender or location. For example, EG means for example. urbanicity or school type in the NERS data. So status variable like gender or location, urbanicity, school type. We also have the typical ANOVA regression assumptions of equal variances, independence, and normality for the errors. So, you know, the covariate is the additional X variable. Originally, we started with the ANOVA, for example, gender group, right? So if you have Y hat equals beta 0 plus beta 1, X1, in this case, just X1 is, let's say, gender group. This is just the ANOVA model, right? Since we have only one group variable, gender group, it is called one-way ANOVA. The factor, group factor, has two categories. I mean, don't be confused with the number of categories and number of the way how we call the ANOVA model name. You know, the gender group has two levels or two categories, female or male. Since it has two categories, some students are confused and then they call it like two-way ANOVA. No, it's not true. It has one factor. It has one grouping variable, which is a gender group. So it is called one-way ANOVA. If you add one gender group, I mean one gender variable, which has two categories, female and male, and then if you have one more variable, for example, race, ethnicity group in the model, then since you have two grouping variables, one is gender, the other is race, ethnicity group. So this is called two-way ANOVA. Okay. So, you know, this is ANCOVA model includes the attributes of ANOVA. So ANCOVA model still need to satisfy with the assumptions of ANOVA model here. That's what it's talking about for number 4. Okay. So ANOVA model has, you know, residual assumptions, right? So equal variance assumptions means homogeneity, homoscedasticity, and independence. This residual assumption, IID, EI tilde N, parentheses 0, comma, sigma squares, parentheses. This is IID assumption, right? So in that case, independence, identically IID, identically, independently distributed normally. Okay? Normal distribution, yes. Right? So again, ANCOVA model is a type of multiple regression. So it should include all the multiple regressions assumptions. And also, since ANCOVA has been developed from the ANOVA, ANCOVA should be satisfied with the ANOVA assumptions also. This is what it's talking about. Okay. Now we will see how the interaction is added in the ANCOVA analysis. At that time, it is not anymore ANCOVA, but ATI. Yeah, so if you have this red term, interaction term, this is called ATI model. Again, ATI model is a special form of multiple regression. So ATI model is aptitude treatment interaction model. So that is the acronym, aptitude treatment interaction model. So now we will see how the interaction is added in the ANCOVA analysis. At that time, it is not anymore ANCOVA, but ATI. So this red font shows that this is ATI model. Depending on what discipline that you belong to, some people called this ATI model, some people call multiple regression, some people call interaction regression, some people call ANCOVA plus. model. Doesn't matter. We have visual techniques, specifically, we can make a scatter plot and make markers in SPSS. We did this in 6C PowerPoint, right? So we can plot regression lines for several groups at once. Also, we can compute interaction variables using dummy variables and test their significance statistically. Or one other and quicker way to test interactions is by using the SPSS General Linear Models menu. This is what I was talking about as a shortcut. So you don't need to convert the categorical variable into dummies. You just use the categorical variable as it is. If you use this function, this tab, instead of regression tab, okay? So let's keep reading. Okay, in earlier slides, we examined the public-private school differences on teacher community using a dummy variable, and we included the predictor teacher happiness as a covariate. Using the SPSS general linear models, univariate menu, we will enter teacher community as the dependent variable, the dummy variable public as a fixed factor, and the teacher happiness as the covariate. So in this case, the public, school type has only two responses, public or private, public or non-public. So you don't need to change the dummy in this case. It's already coded as a dummy. We must choose the model button to make the interaction term. This is done by highlighting the variables one at a time and clicking the Build Terms button, then highlighting them both and clicking it again. Okay, once you open the SPSS pull-down menu, so here this is called the pull-down menu, and you see this analyze, and then you read this first one. This is a general linear model, and this is a univariate, and you see this is regression. If you change, for example, G10 urban, it has three categories, right? Urban, suburban, and rural. You need to change that categorical variable into dummies, right? If you want to use this regression function, you need to change that into dummies. However, if you don't want to change that into dummies, and if you just want to use the categorical variable as it is, instead of using this regression function or regression tab, you have to go to general linear model. This is a shortcut. You just go to general linear model and then click univariate and then open this separate window. Then this is a dependent variable and this is your dummy variable G10 urban. Well, in this example, this is a school type public school or private school. So you put the school type here and then here covariate section, and your continuous variable should be here. And then you click this model. Okay. Once you click this model, you have two options, full factorial and custom. You click custom, and then you picked these two variables one by one and move here, and then you want to do interaction and then click this arrow. Then you will see interaction. Then you click these two variables and then drag. At the same time, move this here. Then it will show multiplication between public and whatever covariate here, teacher happiness. So you have three terms. One is a categorical variable, one is continuous variable, and then one is interaction effect between the above. Okay? So continue, click continue. Then now you will have options like you want to see some kind of visualization, adjusted mean, display mean, and you want to move this here. And then you are wanting to know descriptive statistics. Click, and parameter estimate. Click, and maybe you might want to know homogeneity test assumed or not. Levin's test, homogeneity test, do you remember that? In order to check homogeneity assumption, we have two techniques, two methods. One is eyeballing method. You just generate a scatter plot between predicted standardized residual on axis and standardized residual on the y-axis. That kind of scatter plot is to detect the homogeneity assumption is satisfied. Or you simply click here, it shows a table, Levin's test table. So Levin test is sigma of error, sigma squares of error, the variance is the same as all the sigma squares of subgroups. If they are the equal variance, that is the null hypothesis. So if your p-value indicates larger than alpha level 0.05, your data is satisfied with that assumption, homogeneity assumption. So you want to have larger p-value, okay, for the homogeneity assumption. For that assumption, you don't want to reject the null hypothesis, right? If it is violated, then it is a heterogeneous, not homogeneous, okay? So make sure your homogeneity assumption should have a larger p-value than alpha 0.05. Do you remember that? Yeah. And then, you know, whatever function, if you want to have, you just click it for play, you know, and then continue, click the continue. So on the options button, we also will select a number of options. First, we will ask for the means for the factor public. Do this by moving the label public to the display means for box at the top of the options window. Also, we will ask for parameter estimates. This produces the slopes homogeneity test. In this model, we can test to see if the two groups, public and private, have equal variance, error variances. In regressions with only continuous axis, we cannot get this test. Yeah, we are doing general linear model function tab, different tab. This in regression with only continuous axis, we cannot get this table, homogeneous test. We manually click the residual plot. Then you will get the scatter plot, you know, like a normal distribution. Do you remember the plot, histogram plot and residual plot? We did that in the midterm exam. So everything is connected actually, but I'm talking about the shortcut by using the general linear model, okay? General linear model tab. Residual plot, this is the usual plot of residual versus predicted values, okay? here is output for general linear model. So first one, Levin test. This Levin test, so look at this. This is a very high number, high p-value, so we are okay with the homogeneity assumption. Null hypothesis that the error variance of the dependent variable is equal across groups. Yes. So we fail to reject this null hypothesis, which is good. Homogeneity assumption. This output shows the covariate adjusted means on teacher community. These are adjusted for levels of teacher happiness. So do you remember controlling for the other factor? So that means with the same level of covariate, you're gonna compare the means of subgroups for Y, right? So here, with the same level of covariate is here. Covariates appearing in the model are evaluated at the following values. Teacher happiness covariate mean is 0.1456. When you fix this covariate teacher happiness with this mean, and you compare the group means for Y. So here group 0 is private school, group 1 is public school. And then with this covariate mean, then you have this adjusted mean for Y. Teacher community for private school is 2.35. Teacher community for public school is minus 0.553. Does this make sense? And what about the 95% confidence interval? So this confidence interval for this confidence interval for that. So this confidence interval, this statistical significance, the null hypothesis is the beta 1 is 0. Null hypothesis is beta 1 equals 0. Since this confidence interval does not capture 0, this is statistically significant, which means we need to reject the null hypothesis. So that means beta 1 is non-zero. So we conclude minus 0.553 is non-zero. And this high confidence interval, this does not capture a 0. Therefore, we reject the null hypothesis. So null hypothesis was beta 1 for private school is 0. So since we reject the null hypothesis, 2.3514 for the mean of private school is a non-zero. So that's the interpretation of this table. Because this doesn't have a p-value here, so we have to interpret what it is using this confidence interval. So let me summarize hypothesis testing again. 3 different ways. You remember that? Number 1, p-value technique. If your p-value is smaller than alpha 0.05, you reject the null hypothesis and it is statistically significant. And second method, confidence interval method. So confidence interval does not capture a 0. It is statistically significant and we need to reject the null hypothesis. And here there is no test value like t-test, something like or f-test. Okay. Typically, some people memorize the t-test critical value at alpha level 0.05. So t-test value 1.96. So if your t-test value is larger than critical value of t, 1.96, you reject the null hypothesis, and we call it statistically significant. So keep in mind these three hypothesis tests, okay? Here is output for general linear model, all right? So in the regression tables, you see model summary, R-square table, right? And then second one was like F-test, overall omnibus test for model, right? And the third one is individual slope test using t-test, right? Here, this test of between subjects effect, because ANCOVA has been developed from the ANOVA. So the table name is like this, between subject effect. Between subject effect. What does that mean? So let's say we have 30 students in our class, and there are female students and male students, and there are white students and black students, right? So depending on what status is, you know, you can have multiple subgroups in the one class, which has 30 students, right? For example, female students, male students. Let's say there are variations among the female students. So inside the female group, there are variations. This is within subject. If you talk about the variation between female and male, this is between subject variation. You know what I'm talking about? Sometimes between subject variation is smaller than within subject variance. In that case, what happened? In my case, I had kind of strong variation from the average Korean people. So in my case, I have a very high level of within subject variation from my home country people. That's why I left my home country, although I love my country. Yeah. So we have to think about this kind of interesting variations, you know, within subject variation, between subject variation. Okay, here, so intercept and okay, test of between subject effects. This does not use t-test. This use f-test. Public variable, statistically significant because it is smaller than 0.05 alpha. Teacher happiness, covariate. This is also statistically significant because it's smaller than 0.05. We do not remember F critical value unless we look at the F table. So if your test value is not t-test but F table, don't worry about this. You just use this p-value column to decide whether or not it is statistically significant. Interaction effect here, 0.065, which is larger than alpha. So this is not statistically significant. Since you include interaction term based on your theoretical approach, your theoretical, backup theory, this is still ATI model, even though this is statistically insignificant. So whether or not you include this interaction effect is based on your literature review. If you have like a literature evidence to set up your model, then you have to include this one. And then you see what's going on in your data analysis. Even though the existing theory says interaction effect is important, but why my analysis does not show it is statistically significant? There are numerous reasons why there is a discrepancy between the theory and your data analysis. There are really a lot of reasons. Maybe the data is not that good, representative data, you don't know. Or maybe other reason, maybe your estimation technique, OLS technique is not that good. There are other kind of estimation technique, maximum likelihood estimation. And depending on what kind of variable, like categorical variable or continuous variable, and the categories are how many, and depending on, like circumstance that you have in terms of data, like number of sample, you have different estimation technique. I mean, we have a lot of different techniques, but what we are learning is a very basic estimation technique, which is OLS regression. So there are numerous reasons. Maybe your population is not very typical people. Maybe there are all outliers, or they are not that, general population, or your theory is maybe outdated. We never know. But anyway, if you have evidence literature and theories, you have to have interaction effect for it, okay? And then find out what is going on in the statistical result. And then in the last section, conclusion section in your paper, you might talk about, why my data analysis is not consistent with the previous theory says, or you have to connect the, theory and your data and population, all kinds of things, okay? I will post an example study that you can refer to. We have 5 sections for research paper. Introduction, that's number 1. Number 2, literature review and theoretical framework. That is section 2. Section 3, methodology. What kind of analytical strategy do you adopt for your study, and what sample do you use for your population, target population, and what is the sampling strategy was it, because you use the secondary data, you have to describe what the data is, the sampling strategy, and that is for methodology section, okay? And 4th section is data analysis. Data analysis will show what you have learned, how you can apply your knowledge to your data analysis. Okay, so regression and statistics. That's the 4th section. And then final section is conclusion and discussions. And you bring the, literature that you put in the 2nd section, and then you will interpret your data analysis based on the previous literature review. And then finally, you will suggest some theoretical implication or policy implication or practical implication for practitioners, right? And then you will put some limitation over your study. Every study has a limitation, so don't worry about it. So anyway, writing, simple is beautiful. Don't try to make it too fancy. Just make it simple, and then, one sentence should be clear, and transparency is really important. And you have to write it very honestly, okay? Another way of saying that there is no covariate, X means here multiplication, group interaction, is to say that the slopes of X as a predictor of y must be equal in all of the groups or levels of the factor, we may write for k groups that beta 1 equals beta 2 equals beta k equals beta within. Beta within is a common within group slope. Okay, so regardless of the group, this beta within, beta slope for covariate is shared common mean for all the groups. Shared group mean, that's why within, we will put within. Okay, within, remember that? Within group slope. Okay, this one common slope penetrates all the groups. What slope? This slope is for what? Covariate. Okay. So based on the same mean of covariate, we're gonna compare the group effect on the y outcome. Okay. This is the slope we will estimate in the ANCOVA model. This is why we need to look at the model with an interaction to check whether we need it in the model. So even though you finalize your model as an ANCOVA model, you first check interaction first. Analysis of covariance, selecting X. So this is the ANOVA model, F-test. This F-test result, overall model F-test is this. And in this general linear model, the table of test of between subject effects, the corrected model is exactly the same as this. This ANOVA model is from where? When you use a regression function, regression tab, you will have this ANOVA for model, overall model test, right? Here, when you use general linear model tab, not regression tab, you will have this one single table, test of between subject effect. Then overall model is shown inside this table, actually, okay? So you see this residual is the same as this one. Interesting, right? So if you want to double check your analysis, when you run GLM model, you have this result. And then you want to run the model one more time using regression tab. And then your overall model test using this ANOVA table is exactly the same as this. Okay. And now here inside the slope test is still shown as F-test here. If you run a model using regression tab, you have a coefficients table with a t-test, right? After this ANOVA table, you have one more table, which is called coefficients. That is a slope test table, right? Actually, in the general linear model, this one single table shows everything. This is a model, overall model test, and this is the error, mean square here. And then in the medium, inside the table, you have three slopes, significance test here. And then interaction effect is actually insignificant, right? So let's read this one. The source table in the top is from the regression menu. The same info, but more detailed, was shown in the GLM output. Yes, this table has more information than this. This is just the model, overall model test only. That doesn't show any individual slope test. You have to see one more table if you use the regression menu. Okay. Anyway, the interaction is not significant, so we can omit it. So even though the slide said the interaction is not significant and you can omit it, then I don't agree with it because I'm a theorist. So you have the same approach than I have. This is a statistical approach. If this is not statistically significant, a statistician just remove this interaction effect from the model. But in public administration, we set up our model based on theory. And once you run the analysis, even though the one single X variable like interaction effect is not statistically significant, then you have to think about why this is not statistically significant. And then you have to discuss it in the conclusion and limitation section. But statistician does not have any theoretical background in context, what we are doing, and in themes, what we are dealing with, right? So if statistically this interaction effect is not statistically significant, then statistician is just eliminate this interaction term. That's what they normally do, but we do not do it, okay? So this coefficient table is shown in regression menu, right? So now teacher, public, there are only two main effects, not including the interaction effect. Because statistician's approach, because it shows here, it's not statistically significant. So the analyst removed the interaction effect. Now the model has only two slopes. This is a GLM model table, and let's go back to the previous slide. This is a regression model table for model test, overall model test. This is GLM, general linear model table. This is a regression menu table for individual slope test. This is a general linear model, individual slope test. Of course, general linear model has individual slope test is here, but this is for between subject effect rather than t-test. This is not t-test, right? So now general linear model tab also shows a t-test here. So t-test here, interaction, teacher, happiness, and then this is school type. So you do not see interaction effect here because the statistician removed the interaction effect because it was shown as insignificant. We do not do it. We still need to include that, even though it is not statistically significant. The slopes in the top table are from the regression menu for the model with no interaction. The same info is shown below in the GLM output, GLM menu output, though the sign for public is reversed. So sign public is reversed. So it depends on what the reference groups were. In this case, your coding shows public 1, private 0, but here parameter was set up 0, which means when you have equation model, you plug 0 in the x, then the whole term becomes 0, right? Because the slope becomes 0, so then the entire term is 0. So here, the SPSS set up, public school 1 was a reference group. So with this reason, the sign of this is opposite. In this case, public school, this is a public school, and private school, parameter estimate is 0. Does it make sense? So, in consequence, they are the same result. All right. So once you see this kind of mathematical model, then some people can be freaked out. No need to, not necessary. Let's make it simplified. Whenever you see some complicated thing, try to make it simplified. So this is a traditional one-way ANCOVA model. So one-way ANCOVA means this alpha. Now this form, this notation is like ANOVA model. This is ANCOVA model, but notation is followed for ANOVA form. So if you see mu, this is grand mean, and alpha is group mean. So if I change this into regression form notation, then you can say beta 0 instead of mu, beta 1 x1 instead of alpha, plus beta 2 x2. So this whole parenthesis part is x2, and plus residual. Okay, so it's nothing different from that regression form. Why do we have this kind of complicated form? Yeah, because the ANOVA is the starting point before we learn the ANCOVA. That's why typically most statistics textbook use this ANOVA form. Anyway, can you write down the form regression type notation? So y ij equals beta 0 plus beta 1 x1 plus beta 2 x2 plus eij. That is exactly same as this, okay? This type of notation is ANOVA form, and what I just talked about is yij equal beta 0 plus beta 1 x1 plus beta 2 x2 plus eij is regression form, all right? So y is y outcome variable, okay? Y outcome variable. And xij is covariate, continuous variable, covariate, okay? Covariate score over I person, okay? So don't think about this one, it's way too complicated. Anyway, so mu x is a centering constant. So this is kind of centering technique, but what you need to remember is just that this is x2, mu grand mean for y beta 0. So beta 0 is usually reference group mean. Okay, reference group mean. Okay, grand mean of y in the population. Alpha is a J treatment effect in the population. So you have a gender group, even though it says a treatment, you know, you don't need to think that way, treatment. You know, status group, let's say J is gender. Then you have two groups, female and male. So alpha is beta 1 x1. Okay, so the Jth treatment effect in the population. So mu J means mu, if you say mu 1, mu 2, then J is 1 and 2. So mu 1 is male mean, mu 2 is female mean, and then male mean minus the grand mean. So that is a group deviation, group difference, right, from the grand mean, right? And then mu 2 female mean, female mean minus grand mean. So that is a female group mean difference from the grand mean, right? So that's why we call it group effect, with controlling for other factor, okay? the same interpretation, okay? So this is not that important, okay? Because the logic is the same as before, same as what we have learned before. You know how to interpret the parameter and X variables, right? In the multiple regression. So that is exactly the same. So don't be confused. Don't try to be confused with this kind of different notation, okay? Analysis of covariance, the model. So beta within the slope of covariate in the population, which is the predicted change in Y given one unit change in X with group membership held constant. So held constant. So same. Okay. Group memberships, regardless of female or male, they share the common mean for the covariate. That's what it is. Okay, this is a residual. W label on beta represent the within group slope. That is, all groups must share the same population group for X, predicting Y. Also note that beta within is multiplied not by the X score, but the deviation of the score from the mean of X, mu X. Also, the intercept is not quite the same as in regression. ANCOVA model produced by GLM differs a little. It is Yij. So this is the same as this. But the notation, look. If you have dummies, instead of just one single group factor, okay, you can split it in this way. So beta 1 dummy. So if you have urbanicity, G10 urbanicity, so beta 1 D1 is urban, beta 2 D2 is suburban. Okay. If you have a G10 urban, this is a G10 urban categorical variable, but you can split this into dummies. And then this is it. Okay. This is the same as this. Okay. If you have any questions, just email me, okay? Dummy variable for group J, yeah. Dummy variable. So you can read this. Also, we use Y bar, adjusted mean Y. So that's what we try to get by using ANCOVA model. Mathematically speaking, adjusted mean is this. Okay. So this is naive mean, and then you have to subtract the portion of covariate part, covariate portion. Then you will have adjusted mean. Okay. All right. So summary, assumption. We have already discussed the assumptions. X relates linearly to Y. There is no covariate by groups interaction, and the factor does not influence X. The X relates linearly to Y. There is no covariate by groups interaction, or beta J equals beta W within, where beta J is the slope in group J, and factor does not influence X. However, as usual, we also have assumptions about the errors, the IID assumption, Levin's test for the variance equality assumption, normality, residual histogram, independence, but independence assumption does not have any statistical test or plot. Homogeneity Levin test. Since this is larger than 0.05, we are okay with the homogeneity assumption. First step in the ANCOVA is to test whether the covariate has the same slope for each group in the vector. One of the key assumptions of ANCOVA is that this interaction does not exist. Yes, so it is ANCOVA model. If it has interaction effect, it becomes ATI model. If there is an interaction effect between the group and the covariate, then we must first run the ATI or aptitude treatment interaction model or ANCOVA plus. We may begin by plotting the slopes for different groups in a scatter plot. Then we will work through a complete example using the SPSS GLM menu. All right, so based upon the 6C video, please find out how to generate this kind of plot. Okay, so they are crossed, or at least disnominal, disordinal. So I assume they look like there might be an interaction effect. So interaction effect was here added. Okay. Once you add the interaction effect, you can see this statistical test in this test of between subject effects. And you see this is not statistically significant. So even though you have suspicious feeling and the interaction effect existence, but once you run the statistical analysis, then it is not. This is optional, so you can see the degree of freedom. I left this slide set here for the advanced level of students. This is a formula for F-test, mean square and sum of square. Rather than explore this matter further, we will return to SPSS and eliminate the interaction. We can just select the full factorial option on the model button, or we can keep using the custom model but omit the interaction term. Again, here is the Levin's test now for the ANCOVA model. So Levin test for homogeneity. Okay, this is larger than p-value, so we are okay with the homogeneity assumption. And first, continuous variable and grouping factor, both of them are statistically significant. Good. R square is 0.023 and adjusted R square in this multiple regression 0.02. Okay, so you need to report adjusted R square, but this is very tiny. Okay, just 2%. Again,